Let's get started. We're going to finish up optimization today, talking the rest of the way through the whole successive search, implement it, and then we're going to start in on interpolation. The homework is available now. Sorry to put that delay. Try to get this done. Are there any questions, comments, or concerns? Just to go kind of back through what we were doing before, we're going to use a bracketing algorithm or come up with a bracketing algorithm to find basically the minimum or the maxima of a particular function. So we're going to do that is we're going to pick a bracket. So again, the advantage of a bracket is just has to have a single minima or maxima in it in between this. The toughest thing about this is that we don't have the fact that we're trying to find roots to help us out. The roots, again, it was simple to just evaluate the function at the ends of our bracket, and if they have a different sign, in bracket, we knew that we could continue on. Actually check exactly which bracket, new bracket, by bisecting that old one. Minimization is not so nice. Can't easily check that, but as we saw last time, there are some use. Have these sets of conditions. So we have 4 points here. So we're going to have to come up with three points and then 4 points. And we can see, given these 4 points, where the minima is in relation to them. And then we can also actually use the, if f is less than, f of x1 is less than f of x2 in this case, so it's checking these 2 points for all of these. And there's 2 cases. One that's always x0, x2 is the right bracket. And then the other one, if it's the flip, is x1, x3.
It was not.
Okay, great.
Yeah, it's batteries.
We kind of actually did this, but as long as that's on.
Yeah, thanks. So this is actually giving us an ability to actually just use 2 points, the evaluation of those points, the minima or maxima of those 2 points. But notice that there are a lot of cases. It's a bit more complicated, but the actual ability for us to decide which bracket to use in the next iteration is there. So this is a core part of the algorithm, but we still haven't decided where to put these points. Bisection was easy. We divided the interval in half. Golden-Saxon search is a little bit more complicated. So we defined a bunch of things. My slide's way over there. So we have a bunch of distances, and these are going to help us kind of do the mathematics of how this is going to come out. And we require 2 different things. One is that the 2 new possible brackets, so these are overlapping brackets, recall, we want them to be the same size because that's just seems a nice thing to do. And in fact, that's actually important. So otherwise, we could get into trouble. We may not converge as fast. So there's an optimality condition kind of sitting behind here. And we also want to say that the distances between subsequent triplets is proportional. Okay, so that's a little bit of a mouthful. So really what it's saying is, again, we have 3 different points we're getting at each iteration, and then we pick a 4th point. But those 3 points, as we go down, we want them to have all their distances between them, so there's 2. We want them to be proportional. So in particular here, we want them to be proportional in a particular way such that these 2 conditions are going to be satisfied. And as that's going to lead us to golden ratio, we'll see how that is. So here's 2 pictures of these 2 new brackets. So I'm starting out with x0, x1, x0, x1, x2, x3. We have 2 different brackets, x0, x1, x2, or x1, x2, x3. Okay, so that's the distance in green and the distance in red, and we're requiring those to be equal. The subsequent distances between each of these points, we also want to be equal. And we are also going to pick, so x star would be our next piece of our bracket. So we're actually, in these 2 pictures, x star is going to be on either side of these things. We want that distance in blue to be proportional to the distances before. All right, so all this is kind of coming down to say is that we want things to be shrinking in a nice way. We don't want to be overly zealous about how we're actually shrinking these things. And that actually is going to lead us to exactly how we're going to construct these brackets. So we have a condition on which bracket to choose, and then how to choose a new bracket to evaluate as well. So how does this work? Okay, so the first rule, this is just some algebra. We say a plus c is equal to b. Okay? So if we just write out what a and c are, so a was the distance between x0 and x1, b was between x1 and x2, or c was x1 and x2, and b is x3 to x1. So there's really 4 different distances going on here. If we write that out and we have a relationship between these, because we have the x1s canceling out, we see x2 minus x0 is equal to x3 minus x1. Again, let me just flip back here. These are the distances as they're defined, so we're just using those. We just defined them previously, and then keep in mind that those distances are, of course, these blue, green, aquamarine, green, and red distances. Okay? Move this over here so I don't keep on going back and forth. Okay, so we're going to say that this is going to allow us to pick x2. And then we're going to choose how to pick x1. You could do the opposite. You're going to get the same answer back out. It's just a matter of we have to figure out these 2 new points. Okay, so we have x2. We're solving for the rest of it. All right, now what happens? The proportionality implication. So we've used one of our conditions, and now we're going to use the proportionality. The proportionality says that if we have these ratios, a over b and c over a, if we're going to pick one of these brackets, so that's bringing in the subsequent piece of it, if we're going to have the condition fx1 is less than fx2, we're going to pick the bracket x0, x1, x2. So x0 to x2, it just includes x1. And these are the distances that need to be proportional to the new distances. So note that we're actually using the new distances and comparing them to the old, okay, using these ratios. And similarly, you can do the same thing, and it just happens to be the other bracket, and you're going to get these distances. So again, you can use either one. This condition that we've already chosen is going to tell us which one to use, but we want both to be true, regardless. We're going to go forward. All right. So ratios, when you're doing things like this, where you will have some sort of sequence getting smaller and smaller, where you have some sort of equality as you're going down, this often leads to the golden ratio. You think about spirals. That's a continuous version of the golden ratio as you go down inside that spiral. So that's kind of the very hand-wavy kind of intuition for this, why this is happening. But here's the mathematics of it. We can just do some algebra, okay? So we have the step where we're just going to eliminate c. We have both equations. We want both of these to be true, by the way. That's actually very important. We're going to use both of them. So if we plug in, we eliminate c, we have a and b. Those are distances again. We rearrange a little bit, and we get down to this here. Okay? So there's lots of places to go from here. One is to notice that there's a variable here, b over a, and then that's a quadratic formula, and we can solve for b over a. Okay? And that's what we do here. And it turns out the roots of this equation are exactly, well, one of the versions of the golden ratio. 1 plus or minus the square root of 5 over 2. Okay? So this is really just coming from the fact that we're requiring these distances like this, and they have a relationship between the two in that they have to be equal or proportional. Okay? Now, why is this important? Well, it's the name of the algorithm, so it's nice to know why it's called that. Otherwise, it's a little mysterious. But the other thing that's nice about this is that since we know what the golden ratio is, and we actually even have some constants defined using it, we can use this instead of all these rules to define our new brackets. So every single time we go down, we can choose them based on the golden ratio rather than actually computing these distances. Okay? All right. So I encourage you, this is by no means, I'm going through this somewhat quickly. This is algebra. So go back and try to convince yourself. The distances themselves are a little confusing. I've tried so many iterations of trying to figure out ways to explain these distances. I think it's just best to sit down and draw them out and then stare at them for 5-10 minutes, and you'll hopefully get what's going on. All right. So we have the golden ratio now. Now we're going to talk about how we're going to pick these points and relative to the golden ratio, because now we have the distances. Now we have to go back and figure out the points. So we're going to say the new bracket, whatever it's going to be, is going to be hat variables. So x hat 0. In the case that we're going in one direction, that's going to actually just be x0. So we're choosing the left-hand side of bracket. X2 hat is actually going to be x1 now, because we're translating it over. And this is all important for our algorithm, because we're going to have to reassign these variables every single iteration through the loop. And then x hat 3 is going to be x2. So the new bracket in this case is going to be the left one, and then those are going to be the new variables from our last iteration. So we can label them again like that. We still have one more point to get out. We still need x hat 1. And we can use the golden ratio by the fact that we know a, and there's a relationship between a and a hat, because we always want this to be the golden ratio in between these two. That's the proportionality going down. So that's a nice way to define it. Now we have a relationship between x1 and x0, because that's what defines a, or a hat in this case. And then we can say, well, that's simply because we've defined it up here, x hat x0. We can just replace that. And the same thing, x1 is right here. So, and we already know what x1 is, right? That's not a hat variable. We can solve for x1 hat, and we get this. So that's the subsequent picking of the brackets. Okay? That's just for the left-hand side one. Okay? The other direction, so we're taking the right-hand bracket. We have x1 and x3. So x3 doesn't change again, right? It's what's the endpoint. X0 hat is actually going to become the old x1. X1 hat is going to be the old x2. We're still left over with x2. You've got to look at the things I don't have defined. And the same thing happens. We know that there's a proportionality between the new distance c and the old distance c, so c hat and c. That happens to have to do with the golden ratio. We do a little bit of math, and we can solve for x2 hat. Okay? So most of this is just reassigning, and then because we know the golden ratio is involved, we can use that to actually define the one point we actually have to come up with that's new. All right? So actually going back to this picture, again, we have x0, x1, x2, x3. We're picking, in this case, what I'm marking as star. That's how we're getting that point there. So depending on which way we're going, the left-hand one, I'm picking the left-hand bracket. The right-hand one, I'm picking the right-hand bracket for the new x star. Okay, so that gives me, if you want to look at it this way, x0, x2 will be the new x0 and x3. x1 is going to be the new x2, counting 0, 1, 2, 3, and then the new point's x1. Similarly, on this side, it'd be the new x0 is x1, the old x3 is the new x3, the old x2 is going to become x1, and then we have a new point. So it's just that new point, and it has all to do with the fact that I know this distance has to be proportional every single time I go down. Okay? So that's golden section search, but what's the algorithm look like? Got to have an initial guess. We have an initial bracket. we initialize the points. So at the beginning of the initializing of the bracket, we want to start out on a good foot. So we choose both of the new points using this formula, which is related to the last one we saw. Then we enter the loop. We evaluate our bracket criteria. So we figure out, are we going to use the left bracket or the right bracket, just by evaluating f. And then depending on which one's less than the other, we're going to pick the bracket and pick the new set of brackets inside of the one new point, really, that we have to calculate. Okay? And then there's all sorts of things to say, I want to stop, because there's never one particular answer to this. You can check the bracket size, but note that you can't actually check if we're close enough to 0 anymore, because we no longer have that criteria. That's kind of one of the hard parts of this. So oftentimes, just picking the tolerance on the bracket size itself, or another way to say this is, are you changing, are you getting closer, are you changing where you're looking by a certain amount each time? If not, then you can say, I'm done. So hopefully that gives you an answer. Okay. There's lots of guarantees on this working, which is nice. You know that as long as this was a true bracket, that you will eventually get down to the minimum. That has to do with the rules we've specified, the proportionality and the equality. So this is all kind of seems overly complicated, but it's important due to the fact we can't actually check exactly where we are. Okay? We have to be a bit more careful about that. Yeah?
That phi there, that is the old ratio?
Yes, yeah. One of the versions of it, depending on how you define it. Yes, yeah. It's just as a constant proportional number. Okay, so I don't know why I did that. We have the same function as before when we were doing interpolation, or the interpolation methods. So now we're going to try to do golden section search. So I do want to give you a few minutes now to kind of go through what we just did. There is a bit more code here to do. It's just a few if statements, and that's constructing that x. Note that I've computed phi here. For some odd reason, I think there's a NumPy version of this constant, and it's not that number. So there is two different ways to actually calculate this particular thing. So just be aware of that. It's important to choose the right ratio. But we got there. We have the algorithm pattern parameters. We have to initialize this, like we just said, and then we have to go through the iteration. Okay? So I want to give you a few minutes for that. Either try to code it up and think about the algorithm itself, try to convince yourself that what's going on seems to make sense. We'll finish this up, kind of test it out, and then finish up our discussion. Okay, so yeah, I'll give you maybe 3 minutes for that. Okay. So we kind of have two jobs here. One is to initialize the original bracket, which the way I programmed this up in the notes is to just have x be my bracket. So just so it matches exactly the algorithm I described. And I've chosen 0.2 to 0.5 to be my initial bracket. Okay? And just looking by inspection, going up here, you can see that this is going to get this minimum here. Note that we're looking for the minimum here. Things flip. The signs on things flip a little bit. It's the same exact algorithm. You just want to change the evaluation of f, whether it's less than or greater than which one you're choosing. So we'll do that. Then we need to fill in the middle ones. Again, I'm just creating a list. You could use a NumPy array as well. And I'm putting none into them. That's the Python equivalent saying there's nothing here, don't use me. So it actually will give me an error if I try to do a bunch of stuff to it. Of course, we're going to be perfect programmers right at the beginning here and fill these things in. So x1 is going to be looking at this piece here. Like so. I think I got that right. I am actually looking at my formulas on my left here so I can make sure that I can type them correctly because this is not big enough. There we go. And then we have x2, that other middle point is defined similarly. Like that. Okay. So these formulas, if you look at them, what we're really looking at is that we're actually creating two ratios, right? We're creating the ratio of x1 and x3, and then a ratio between x3 and x0, the distance between here, and it's being multiplied by phi. So again, this is the proportionality piece of this coming in to define these things. Okay, so let's go back into our main loop. So this is, again, the similar type of loop from before. I'm just plotting some things so we can watch what's going to happen. And then we have some loop. It has a max steps, so we don't go into an infinite loop. And I'm going to keep track of the success of the algorithm by this success equals false. And I'll set it to true if I think I've accomplished my goal. So the first thing we're going to do is actually evaluate the 2 points. So f1 and f2. Because those are going to, the sign, or which one's bigger than the other is going to determine what I'm going to do. Note that if these were equal, something bad's happen. I didn't have a bracket to begin with, because if they are equal, something's flat, which means I could be in trouble. I need a actually more advanced algorithm at that point. Or I actually have multiple minima in my bracket, in which case I've chosen poorly. So we're going to do that. There's another piece to this that I will say. You can reuse f1 and f2 just like we reuse x. I'm not going to do that just for clarity's sake. But that's obviously something you could do as well to save some computation. So here's our primary check. Okay, so this is going to be the left bracket. So maybe we want to just label it that way so we know. So now I'm going to actually store the new bracket in its own list. And that's because I'm going to have to use the values a couple times. So I don't want to overwrite my old bracket right away. So here I'm just going to use x new. There's multiple ways to get around this, of course. Okay, so here I'm creating a new list. It's based on the old parts of it. I'm just choosing and moving things around. So this is a nice way to kind of just write exactly what's going on. And then x new 1 is going to be the one based on the ratio. For some reason I typed this in differently than before. Let's put this over here. All right. Ow. Technically speaking, we have to go out of the building. Found that productive. I got coffee. I don't know. So I'm not waiting around for this. Okay. I'm sorry that was rather shocking, the noise. It's not like that in most of the building. This is probably not a safe thing. Yeah. It's Amber Alert. This is quite a day. So let's try to get something done and get through this lecture at least today. So we ended up, we had just coded up the left bracket piece of this. And so we do need to do the right bracket now. So we'll use an else statement. This does imply that we are taking into account F1 equal to F2 using this. That doesn't necessarily mean it's going to work, just to be clear. But we do the exact same thing. In this case, we're going to have x1, x2, non and x3, and x new, count is x2. So here we'll do x2 plus x2 minus x1 divided by phi. I did that right. Okay. So no, we actually haven't put x new back into x because we had to use it for all the values that we had before. So once we've actually done the bracket business, we have our new bracket, and we can simply say x is equal to x new. Okay, and that would handle either case. We're not quite done yet. We have to also check for our tolerance. Again, you can do all sorts of things here. In this case, I'm going to do the one that I had, which is the size of this bracket. If it's less than the tolerance given, I will say success is equal to true, and then break out of the loop, because we don't have to continue anymore. All right. So there's a bunch of different things to be said here. For instance, I'm saying that t star, so t star would be the minimum. In this case, I'm just taking the bracket and dividing it by 2 and saying that's close enough. So just keep that in mind. There's other ways to do it. You could just pick x2 or x3 once, or yeah, well, x1 or x2 by the code. It doesn't, I mean, at this point, we're going to say the tolerance is closer to the minimum, that it doesn't really matter which one you're choosing. So we can do this. And you can see these are the black points. The black points are just being plotted as we narrow down our bracket, and they do converge onto the bottom of this, this minimum. And it's fairly fast. Its number of steps is 17. Actually, I don't remember what the interpolation version did. Oh, I broke it though. Okay. I broke it, but I don't know how. That's always encouraging. Oh, I don't have any code in there. All right, well, that doesn't help us, does it? Let's actually go to the full notes real quick. All right. So you can see in this case, actually, the interpolation did do better than this golden section search. Interpolation doesn't work all the time, whereas golden section search has a much broader application. You're more guaranteed to get the right answer. So play with this, find other functions. There's all sorts of interesting examples. You try out a bracket which has 2 minima in it. That's an interesting test case as well, just to understand things. Just to kind of finish up here, SciPy has an entire package dedicated to optimization. It's not the best, but it works, I would say. Most of the best optimization algorithms today are primarily commercial, unfortunately. But SciPy optimization will at least get you a head start on it. And just to show kind of what it looks like, there's some of the things that are here. You can do import scipy.optimize, and then here's the golden section search, actually already implemented for you. You give it the bracket of the 3 points, and you're done. Okay? And it gives us about the same type of answer. In order to just actually look at this, you can say optimize .tab, and you can see all the different types of optimization in here. There's a huge amount of them, including things that deal with constraints. So constraint would be, I want you to minimize this function, but I don't want an answer that's less than 1, for instance. There's all sorts of other more complicated versions of that. If you want to see the entirety of the package, because there's a lot here, pull this up. See different ways to, in general, minimize something. You can look at how to define bounds. You can see that there's scalar versions of the golden section search. Brent, we didn't talk about very much, but it's another example of that. And actually, this also includes various root finding algorithms as well, down here at the bottom somewhere. So here we have another Brent bisection, Newton. If you have to have a calculation for the Newton, the derivative, this is actually a much more complicated way to do it. Of course, multidimensional things as well, which becomes even more complicated. So there's lots of different things here. It's a pretty deep field. And again, there are courses entirely dedicated to optimization that you can take. And if you are interested in this type of stuff, I definitely suggest looking into it. Yeah?
What was the comparison you just made about interpolation?
So I think it was 17 steps for golden section search and then 6 steps for the interpolation. I think it was using the same tolerance too, I think.
So like,
Well,
does it work better?
so in principle, we don't know which one's going to be better necessarily. Usually what happens with these interpolative types of approaches is that they don't work for some of the cases, whereas golden section search is much more robust. Similar to the bisection. Bisection, actually, if you do have a bracket, you know it's going to converge, whereas Newton's method may not. So that's kind of it's the trade-off between the two. So yeah, so that's optimization and root finding. Are there any questions before we kind of leave this topic? All right. Close a few things here. is super tiny. Okay, so we'll just kind of go in a little bit into interpolation today. We've seen it a couple times already. So now we're going to do a deep dive into interpolation because it does form the basis of a lot of our methodologies. The key idea behind interpolation is this definition. You were given a set of values, so x, y pairs. In this case, we're going to use y as the data and x as the locations. So x is the independent variable, y is the dependent variable. An interpolant is some function. Doesn't really have to be continuous, although we're going to require that. It's some function that passes exactly through the data. Okay? There are lots of ways to choose that function. If you wanted to connect the dots, if you connected the data points y and x, all I'm required is that my function that comes out of this thing is going to satisfy f of xi is equal to yi. Okay? So lots of ways to choose it, and that's going to be the kind of core of this discussion. And we're going to get to some of the more generalized ideas, including regression, at least a little bit of a dip into regression as well. But keep this in mind, because this is very important. There's lots of consequences to requiring this particular thing. So interpolation is good for all sorts of stuff. We're going to use it as a kind of the back end of a lot of the theory, because if you say I have an interpolant, it's a reconstruction or an approximation of the function. That means I can talk about Taylor series, especially for polynomials, which is exactly what we're going to do. And then we can talk about how we act on that finite Taylor sum and how that differs from the Taylor series. So that's going to be a huge component of a lot of this. There's also various things we've seen. We've seen root finding, which could be looked at as an interpolation scheme. We saw optimization. Numerical integration and differentiation are also often predicated on interpolation. So there's lots of different pieces of this. Kind of forms a larger field called approximation theory. So again, something you can take an entire course on. So we're going to touch on kind of the high points in some of the theory that we're going to use later in the course. And we're also going to restrict ourselves, at least for the beginning part of this, to polynomials. As I said, polynomials are nice because we can do things with them. We understand them. We can construct Taylor series. In fact, a Taylor sum is simply an interpolant at one point that maybe we want to have more than one point. We'll get to that a little bit as well. But we basically have a polynomial of degree capital N. I'm going to use this math calligraphy P, capital N, to represent a polynomial interpolant. And it's going to pass through n plus 1 values. So I'll try. I think I'm more consistent now. But basically, we're going to have n plus 1 values if it's a degree n polynomial. Think of it this way. If we have a linear polynomial, that's a degree 1 polynomial, which means I need 2 pieces of information to create that line. Okay, so it's always off by 1. But there's another piece to this that's very important, and that's that there's a unique polynomial. Now, why is it unique? There's lots of reasons for this. One that we've kind of seen already, or we talked about a little bit, is the fact that if I create a system of equations for this polynomial to solve for the coefficients, we'll do that a little bit, I have exactly the right number of unknowns if I require this, okay? Which means there's a unique solution to that system of equations. Okay? So that's going to come up in a couple other different ways too as we go along. But let's kind of ground ourselves a little bit and go through some simple examples. So we have 2 points. We have x0, y0, and x1, y1. That would lead to a polynomial interpolant, p1 x plus p0. And we want to find the 2 points, p0 and p1. Right? This is an equation for a line. This isn't hopefully too surprising. Actually, let me bring this up so I don't skip something interesting. Okay, so we can solve for p0 if we have x, y0, and x0. So that's one equation that we solved for and inverted. We can kind of do this in any sort of order. We can write it, would be a point slope form maybe. The reason why I'm showing you what may seem kind of a trivial example is that we're going to see polynomials that we're going to construct look like these and generalize to any degree polynomial by constructing certain bases, which will be important. Okay. So this is the equations for the line. So 3 points. Oops, one more. Oh, actually, I do have a point to make the other. So here you see we have y1 minus y0, x1 minus x0. That's one of the coefficients for x. Okay, that's one way to write it anyways. And then we have plus y0 minus y1 minus y0, x1 minus x0 multiplied by x0, okay, which simplifies back down to the thing we had. This is a particular basis of polynomial. Okay, keep in mind that form. 3 points. Have a quadratic, second order or second degree polynomial. We have 3 unknowns, the p's, and we have 3 points. Okay, so we can do this. It's a little bit more algebra. These are our equations. Note that these aren't nonlinear equations. It's not actually important that we have a squared, like a quadratic. That's actually taken out because we know exactly x0, x1, and x2. It's the polynomials which multiply, or the polynomial coefficients that multiply. So this is still a linear system of equations. It's just more complicated than the last time. But this is already, like, it's going to take you a little while to do this by hand. It's a 3 by 3 matrix you're trying to invert. You can write that down. It's not that big of a deal. But it is going to take some time. Okay. So maybe we don't want to do it like this, but we know we can do it. So just to kind of put us on a basis, from linear algebra, we expect, because we have these linear systems, that these should be unique just from various theorems from linear algebra. But another way to look at it is we can just plug this in and look at and assume a contradiction. Okay? So I'm going to define my polynomial. It's going to be capital N degrees. So here's just the definition of it. Note that n is equal to 0. The beginning of the index is 0, so we do have the right number of terms. Here it's all written out. And we're going to require that it's an interpolant. So this is the statement from before, saying that my interpolating function, which in this case is Pn, if I evaluate it at my data points, my x data points, is equal to my y data point. Okay? So that has to be true. So now I'm going to assume that there is a polynomial that exists that does the exact same thing. Okay? So that means that Q, I'm going to just define some other polynomial, the QNs or some other numbers of some sort. So any of the QNs could be different and this would work. And then I'm going to say, okay, well, this is also an interpolant. So QNXI is equal to YI. And then I'm going to say if these are different functions, then their difference should be non-zero, somewhere non-zero. Okay? And that's going to be t. Okay, so I've defined a function Tn, which is the difference of these things. So going forward, we know that by definition of an interpolant that at the xi's, t also has to be equal to 0. But that's not so surprising. We're requiring these to be interpolants. So that that really can't be changed. But what about the rest of x? If I just write down what these things are, I come to this expression, Pn minus Qn times xn. Right, so this is the polynomial Tn. If Tn xi is equal to 0 at the xi's, at one spot, note that there is no spatial dependence on those coefficients. So that means that these have to be actually identically equal to 0. If they're equal to 0 in this case, they have to be equal to 0 in all of x. And therefore, these are the exact same polynomials. Okay? This is not to say that you could use a higher order polynomial, put it through those points, and not get something back out that is different. That is completely the case. But for a particular degree polynomial, how we're looking at it now, there is a unique polynomial that does that. Okay? And this has, I mean, there's a lot of depth to this, a lot of other things you could say or ways to say the exact same thing. For instance, this is related to the number of roots of a polynomial. Even if they're identical, you still get back out that they're going to be equal to a certain number of points, or the difference between two polynomials is going to be equal to 0 at the roots of that polynomial. But this is a fundamental thing, because this is going to actually say that any representation of a polynomial of degree capital N is and it's an interpolant, then it's going to be a representation for all polynomials. They're all going to be identical. Okay? Now, the real reason we're going to use this, at least the beginning part of this, is that there's a bunch of different ways to write polynomials. Some of them are easier to use than others, depending on what the data is. And we know from this that it doesn't matter how we write it, they're all going to be the same. They're exact same functions. Okay, so let's actually start talking about bases. Okay, so we have different bases for different polynomials. The simplest one is the monomial basis. So the basis is 1, x squared, x cubed, all the way up to xn. And then I have the coefficients out in front of these things, which is basically what I've been doing. I'm projecting onto that basis. So this is getting into a more of a linear algebra type of sense. I have some function basis, and I'm projecting onto that. Okay? Now, as we know from bases, you can have different bases and different representations on that basis, which again is why we're interested in this. Monomial basis is not actually that useful, although it's simple. And we'll see how this is true. But we're going to move on from this, and we know that if we're going to construct another basis, maybe it's more complex than this, the bases themselves, we know that they're going to be identical still. Okay? So this is the monomial basis. It's not so interesting. But if we're actually going to do a projection, so we're projecting some value, like the vector y, the data, we're projecting it onto the basis. So it's directly equivalent to doing the linear algebra ideas of projecting onto a vector, for instance. So how does this look in terms of actually this linear algebra idea? Well, if we take back out and we set up the set of equations, a linear system as we had it before, we have our data. That's going to be the right-hand side of the equation, so the B, so to speak. A is going to be some matrix here, and P is our vector of unknowns. So P0, P1, P2, P3. For this cubic case anyways. Okay. So I can rewrite that as this. So I have a vector x. That's actually kind of the less important value here. So that's just a vector of all the locations, the independent variable values. Y is our vector of data. It's a little bit more important. And then P is going to be our unknown vector. Okay? We defined a Vandermonde matrix as this thing here. Okay? 1's in the first column, the x vector in the second column, the x vector squared in the third column, the fourth column is going to be cubic. And we can extend this as far as we want. If you wanted an n plus 1 by n plus 1, the last column would be, for instance, x to the nth power. But the reason why this Vandermonde matrix is important is that actually this system here is equivalent to the system we were just looking at. Okay? If we actually do the equations back out, we see that these are the equivalent systems. So in effect, what this is doing is it's saying, okay, so if I want to project the data onto my bases, then P is going to be the values representing the weights on each of the basis functions, giving me back my function. Okay, so the inversion of this thing gives me that projection. Well, it's not great. That matrix is kind of dense. It has numbers everywhere, unless some of the x's are 0, which is nice sometimes. But this can get kind of out of hand. If we did want to do like a 5th or 6th order polynomial, this is going to get bigger and bigger. Which is why we generally try to avoid this type of stuff. But this is, this is the most straightforward way to write it down, for sure. So there's actually some interesting questions here, though. What happens if we have redundant data? So what if one of the xi's coincided, which means one of the yi's coincides? Okay? Now, if we have different xi's but same yi, we don't care about that. That's not such a big deal. But if the xi's coincide, we're in trouble, because we have a redundant piece of information. Now, in the linear algebra sense, that means that we have two equations that are actually identical. They don't give me any more information. All right, so now I don't have enough information to solve my linear system. Okay? So again, think about how the column space of this matrix and all that type of stuff is starting to come back to reward us, help us? I'm not even sure. So there's other problems with this. If we have more points in the order of the polynomial we want, well, we have too many constraints. Doesn't mean there isn't a solution, but most of the time there's not going to be. We saw something about that. And then this all comes back down, and we're going to see this again later on, that we're really solving a system of equations. We have the exact same theory from linear algebra about how we can solve these systems and when we can solve them. And this really comes down to the idea that we have a finite basis that just happens to be functions instead of vectors, but has the same type of feel to it. We are out of time. So this is the generalization of it. So, and there's actually a NumPy command to create these matrices, if you are so inclined. So it's not that hard to construct yourself, but that will work. So I will see you next week. I'm trying to remember what day it was. Yeah, have a good weekend.